So let us start with something a little strange. You type, "How do I reset my password?" and the search hands you back the right doc. One that never once uses the word password. No shade words, not one. And it still nailed it. So, how did the machine even know that it is searched by meaning? And underneath it is one idea, an embedding. We take a piece of text and turn it into a list of numbers in a way where the things that mean similar things get numbers that sit close together. We have searched these points before, fast, but today is the deeper question we skipped. How do you even turn meaning into a number in the first place? And why would close together mean similar at all? Because honestly, when you sit with it, this is a bizarre thing to expect. And here is where we are going. An embedding is not the machine understanding your words, it is a position. And it only means anything because the model was trying to make it mean something. By the end, you will know exactly how the training turns into geometry and what is really sitting inside those numbers. Let us build it up. And before we go abstract, let me just show you what one of these actually is. Here is the word cat as an embedding, a long list of numbers 0.17, minus 0.93, 1.42, and on and on. 1536 of them. Quick question. Which one of those numbers mean cat? None of them, not a single number. On its own, it means nothing. So, how does a list of meaningless numbers end up holding a meaning? That is the whole puzzle. Hold on to it. And it starts with a genuinely old idea from linguistics. You know a word by the company it keeps. Let us say, I show you a word you have never seen, tejuno. But I show it to you in sentences. We poured the tejuno. The tejuno was cold and fermented. You already know roughly what it means, some kind of drink, purely from the words around it. Meaning is company, and company is something you can count. So that is exactly how the first embeddings were built. We take a model and train it on one dumb little task. Given a word, predict the words likely to show up around it. That is the whole job. And this is the important part. Nobody ever tells the model what meaning is. But think about what the model is forced to do. To correctly predict that cat and kitten both sit near, purr and litter, and wet, it has no choice but to give them similar internal numbers. Otherwise, it cannot make the same prediction for both. So, meaning is not programmed in, it gets squeezed out. And as a side effect of getting good at prediction, do that across billions of sentences and words that keep the same company drift to the same place. And you can actually watch meaning fall out of nothing but counts. Let us take ice and steam. The word solid shows up about 8.9 times more often next to ice than next to steam. Gas is the opposite, way more with the steam, but a neutral word like water shows up basically equally with both. Its ratio is about 1, and here is the subtle bit. It is not the raw counts that carry the meaning. Every word co occurs with the and water a lot. That is just noise. It is the ratio that carries it. Because the noise, the stuff both words share, cancels out in the ratio, and only the words that actually discriminate ice from steam survive. That surviving signal is what becomes the geometry. And this is where the famous party trick comes from. King minus man plus woman lands you near queen. It is real, but treat it as intuition, not proof. It is fuzzier than people make it sound. The solid claim is just this: relationships between words show up as directions in the space. Hold that word, directions, it comes back. Okay, but there is a crack in the first version, and finding it is the whole leap. Those early embeddings gave every word one fixed vector, one vector for bank, but bank by a river and bank where you keep money are completely different things. So, that one vector is a blurry average of both, pulled to a useless middle. It does not really fit either. So the modern models do something much smarter. The word does not get one vector, it gets a fresh vector every single time, built from the specific sentence it is sitting in. Bank in river bank and bank in bank account come out as two different points in two different neighborhoods. The meaning is computed on the spot from the context, which, if you sit with it, is kind of wild. There is no single embedding for the word bank anymore. It gets a fresh one in every sentence it ever appears in, effectively millions of them. And this really breaks how most people picture it. It is not a dictionary, not a fixed table where you look up bank and read off its one vector. Researchers actually measured this. Even the single best fixed vector you could possibly pick for a word explains less than 5% of how that word's vector really moves around across different sentences. Less than 5%, right? So the lookup table picture is basically wrong. The vector is built fresh every sentence, which raises the obvious question, built how? So, how does a word get reshaped by its sentence? The mechanism is called attention, and this is the actual engine of the whole thing. Let us take a sentence. The animal did not cross the street because it was too tired. Now, what does it refer to? The animal or the street? You know instantly, right? But the model has to actually work it out from scratch. Here is how. Every word puts out three things. A query. Basically, what am I looking for? A key. Here is what I am. And a value. Here is my actual content. To update the word it, we take its query and check it against every other word's key to score how relevant each one is. Then it pulls in a blend of their values, mostly from the words that scored high. So it literally mixes in a bit of animal and a bit of tired and becomes context aware. And watch what happens if we change one word because it was too wide. Now, wide describes a street, not an animal, and the attention shifts. It leans toward street instead. Same word, it, completely different vector, purely from context. That is the machine doing in geometry what you did in your head instantly. And it does not do this once, it stacks this in a model like BERT 12 layers, each with 12 of these attention patterns running in parallel. So the context builds up in rounds. One honest caveat, it is tempting to read these attention links as the model explaining itself, and researchers argue about that. So hold it as the mixing mechanism, each word blending into the words that matter to get it, not as a clean window into its thoughts. So at high level, we have got this powerful context machine now. You would assume its vectors are great straight out of the box, right? They are not. And this one caught me off guard. If you take a raw pre-trained model and just average its word vectors into a sentence vector, it scores worse at judging sentence similarity than averaging plain 2014 era word vectors. The old, dumb method beats it. And the reason ties the whole video together. The raw model was trying to predict text, not to place sentences by similarity. Those are two different jobs. It is good at the first, and it simply never learned the second. So the geometry is in there. The prediction training built it, but it is not organized for comparison yet. It is a powerful, messy space. So we do one more round of training, and it is the same move we saw right at the start, just sharper. We show it pairs. Those two mean the same thing, pull their points together. These two are unrelated, push them apart. Millions of times. This is called contrastive training. And all it does is take that raw, messy space and reorganize it until close reliably means similar. So the raw model was not wrong, it was just untuned. One line for the whole thing. Prediction builds the space and contrast cleans it up. And notice both steps are training. Predict first, then contrast. Hold that it is the punchline we land at the end. So, back to that puzzle from the very start. Remember cat as a list of numbers and none of them individually meant cat. Now we can finally say why. What does number 412 mean? It is the happiness number. Almost nothing on its own. A single dimension is basically not readable. And once you see why, you also see why those similarity scores are slow slippery. Because meaning does not live in the individual numbers, it lives in the directions, combinations spread across the whole vector. Remember, I told you to hold that word directions, this is why. And it is not a vague claim. You can literally isolate, say, a single sentiment direction, one specific combination of the numbers, erase just one direction from the model, and it loses about 76% of its ability to tell positive from negative. One direction carrying that much. So the unit of meaning is a direction, not a dimension. That is the first reason one number tells you nothing. And there are two twists on the top, and both are really saying the same thing. Do not trust the raw numbers. First twist, a few of the numbers, sometimes just one or two, are wildly louder than all the rest, huge in magnitude. And here is why that matters. Similarity is basically the two vectors multiplied together, number by number. So one giant number can dominate the whole multiplication and drag the score around by itself. In some models, a single dimension drives over 99% of the similarity. You would assume that dimension is the important one, carrying all the meaning. It is the exact opposite. Those loud dimensions mostly encode boring surface stuff, like where the words sit in the sentence or punctuation. They are loud, not smart. So much so that if you just turn them down, the scores line up better with what humans actually feel is similar. Second twist, and this is the deep one. Why can a single number not just hold one clean concept? Because the model is trying to store far more concepts than it has numbers to store them in. So it does only one thing it can, it packs them, laying multiple concepts along overlapping directions, sharing the same axis. Picture folding a huge map to fit a tiny drawer. Things end up on top of each other. There is a famous vision neuron that fires for cat faces and the fronts of cars. Two unrelated things, one number, because they got packed together. And the packing is the real reason those scores lie. Everything is little crammed on top of everything. So a raw score of zero point 0.8 not mean 80% similar. The numbers are sharing space. The whole thing is crowded. So an embedding is a distributed code. The meaning is smeared across directions on purpose. More of it than the space can cleanly hold. No wonder one number tells you nothing. One last thing, because it shows the idea is a bigger than text. There is a model called Clip, trained on 400 million image and caption pairs, using the exact same contrastive move. Pull each image and its caption together, push the wrong pairs apart, and once you do that, pictures and words end up on one shared map. So you can type a dog on a beach and get back actual photos, not from tags or file names, but because the sentence and the photo landed in the same neighborhood. To be precise, they do not land on the exact same spot, but far closer than any wrong pairing. Same machinery, completely different data. So we went deep. The company a word keeps, predicting neighbors, attention reshaping a word from its sentence, the contrastive training, and what is really inside the vector. Do not walk away with a pile of names. Because it is all one line, meaning becomes geometry because the model is trained first to predict the company a word creeps, then to pull similar things together. And what you get out of this is a distributed code, meaning smeared across directions, not a table of features. An embedding is not understanding, it is a trained position. That is the whole thing. So here is the shift I want you to walk away with. Every time one of these system tells you two things are similar, it is not comparing their meanings. It is measuring how far training bent the space to put them together. So the next time an embedding does something brilliant or something baffling, you will not think the AI gets it or AI is dumb. You will think, what was this trying to pull together? Answer that and it stops being magic. It becomes a machine you can actually reason about.